The empirical rule gives us a technique for approximating probabilities of events relating to a normal random variable. And this can be really handy if what we're trying to do is get a sense of where our probabilities lie without needing to turn to computers for exact calculations. The big problem with something like the empirical rule is that this is only going to apply if we know that things are normally distributed. And if things are not normally distributed, the probabilities from the empirical rule are not going to be particularly close. And so there's this question where, what if we don't know what distribution our random variables actually hold? What if we're working with quantities that we don't know the distribution of, but we still want to say stuff about their probabilities? Is there anything that we can do? And while we can't make any concrete statements that are as impactful as the empirical rule, there are some statements that we can make about these probabilities. So the empirical rule is going to be a useful tool for approximating normal probabilities, but if the random variable is not normal, it does not apply. And so let's think through a motivating example here. If X represents the blood pressure of some randomly selected individual, we might be interested in, for instance, the proportion of individuals whose blood pressure is outside of some typical range. So let's say that we want to know what proportion of individuals have blood pressure that is more than one standard deviation away from the mean. Now, if X is normally distributed, then what we can do is we can use the empirical rule to say, well, the probability that the mean minus a standard deviation is less than or equal to X, which is less than or equal to the mean plus one standard deviation, is about 68%, right? So the probability that you're within one standard deviation is about 0.68. And so about 32% of individuals would have blood pressures that are outside of this range. And that would be all well and good if blood pressures are normally distributed. But what if we cannot assume that blood pressures are approximately normal? Are we still able to say anything about this probability? And the answer is going to be yes, we can. We're not going to be able to say anything as concrete as it's about 68%, but what we are going to be able to do is actually give bounds on this probability. And in order to do that, we can turn to Chebyshev's inequality. So Chebyshev's inequality is going to apply to any random variable x, whether it's discrete or continuous. And what we're interested in is the probability that we are within k standard deviations of the mean for any value of k. So it does not matter whether k is an integer value or if k is a whole value, right? It can be real numbers between these points, right? Any value of k, Chebyshev's is going to apply for. And so then Chebyshev's inequality states that, and we can walk through here, right? Because there's a lot being written. The probability that mu less than k sigma is a lower bound for x, and mu plus k sigma is an upper bound for x, right? So this follows that empirical rule pattern of being within k standard deviations of the mean. The other way that we can write this, right, and it's very common to use Chebyshev's this way, is to say the distance between x and its mean, so the absolute value of x minus its mean, is less than or equal to k standard deviations, right? So these two statements are exactly the same. They both say we're within k standard deviations of the mean. And what Chebyshev's inequality tells us is not what this probability equals, but instead it tells us that this probability has to be greater than or equal to 1 minus k squared. And so what we're given is actually a lower bound on the probability here. It could be values that are higher than this, but it can never be values that are smaller than this. Okay? Now, the equivalent way that we can state this is instead of saying what's the probability we're within k standard deviations, we could say, well, what's the probability that we're greater than k standard deviations away from the mean? And this has to be less than or equal to 1 divided by k squared. Okay? And so it's the exact same bound both ways, just useful in one case or the other, depending on whether you want an upper bound or a lower bound. Okay? So what we can also do here is we can replace k sigma with some constant. So for instance, if we take, say, k times sigma equals some value, which we'll just call epsilon here, then what this means, right, is that k is going to be equal to epsilon divided by sigma. Okay? And then we can rewrite these probability statements in terms of epsilon. So the probability that x minus mu is, say, less than or equal to epsilon, right? So we've replaced our k sigma with epsilon. That's going to have to be greater than or equal to 1 minus, and then we would do 1 over k squared, but k is epsilon divided by sigma squared, so that's going to be 1 minus sigma squared divided by epsilon squared. Okay, and so Chebyshev's inequality can actually be expanded to say, well, what are the probabilities that any distance from the mean is achieved, right? So that x minus mu is less than or equal to any sort of threshold we want, whether we're expressing it in terms of the variance or in terms of the standard deviation or not, right? And so if we have this, then the probability is going to depend on our variance, but it's the same thing, okay? And so Chebyshev's inequality, we can always think about it in terms of the standard deviations or the variances, right? But we can actually use it a little bit more generally. And the important thing for us to note here is, again, this is only giving us a bound on the probability. It's only going to tell us the probability has to be bigger than some value or the probability has to be less than some value. And for some values, this isn't going to be particularly interesting for us, right? So if we imagine that we take k equals 1, okay? And so if we come over here and we say, let's take k equal to 1, okay? And then we are looking at this probability right here, right? So the probability that x minus mu is within one standard deviation of the mean, right? Then this is going to have to be greater than or equal to 1 minus 1 over k squared. Well, k is 1, okay? And so that's just giving us 0. So what we're saying is that if k is 1, the probability is greater than or equal to 0, that we're within one standard deviation of the mean. We already knew that the probability was greater than or equal to 0 because all probabilities are greater than or equal to 0. And so that's not going to give us an interesting bound. But if instead we were to take k to be equal to 2, right, then we're going to be greater than or equal to 1 over 2 squared. And so now that's going to be 1 minus 1 quarter, right? 1 minus 1 quarter is 3 quarters. And so we can say the probability is at least 75% that you are going to be within 2 standard deviations of the mean, right? And so depending on the value of k, you can have interesting or not interesting statements, but in every case, it's only going to give you a bound on it, okay? It also holds for every distribution and for all k's, whether k is an integer or not. So let's look at an example here. We have scores on a large standardized test. They're standardized so that they have a mean of 500 and a standard deviation of 100. Now, what is the minimum proportion of students who are going to score between 300 and 700? Okay, and so what we want to do in any case when we're thinking about using Chebyshev's inequality, right, which if we look at it, Chebyshev's inequality is going to give us bounds on the probability that x minus mu is, say, less than or equal to k times by sigma, right? And we know that that's greater than or equal to 1 minus 1 over k squared. And so here, right, we know that the mean is 500. And so what we're trying to look at is, okay, well, if x minus 500 falls into some or being below some value, can that equate to our interval, right? And so our interval here is going to be 300 to 700. And so in other words, we want to say, can we write 300 is equal to the mean plus k times by sigma, okay? Or equivalently, can we write 700 is equal to the mean plus k times sigma, okay? And the mean we know is going to be 500, right? And sigma is going to be 100. So we can write this as 500 plus 100k, or we could write this as over here, 500 plus 100 times k. Okay, and looking at both of them, right, so if you do 300 minus 500, that gives you negative 200, and so that means that k would have to be equal to 2, negative 2 here, and in this case, k would have to be equal to positive 2. And so what we want to say is, well, what is the probability that x minus the mean is less than or equal to 2 sigma? And what we know is that that has to be greater than or equal to 1 minus 1 over 2 squared, which is 3 over 4. And so what we're saying there is that no matter the distribution of the test scores, 75% of students will have to fall between 300 and 700, because that means that their distance from the mean is less than or equal to 2 times the standard deviations here. Okay? And so k is equal to 2. An application of Chebyshev's gives us 75%. Right? So 300 is going to be referring to a k of 2, so is 700, right? And so as a result, the probability that you're between 300 and 700 is 1 minus 1 over 2 squared, which is 3 quarters, right? So at least 75% of students are going to score within 200 of the mean. Now, what can we say about the proportion of students who score either below 100 or above 900? And so here we want probability either x is less than or equal to 100 or x greater than or equal to 900, right? And in other words, what we're saying here is if we think about, say, 100, how far is 100 from the mean? Well, 100 is going to be the mean plus sigma times by -4, right? The 100 is 400 below the mean. And 900 here is going to be mu plus sigma times by 4. Put those in brackets there. And so, again, we have that 100 is k equals -4. 900 is k equals +4. But here what we want is we want the probability that the value of x is actually greater than or equal to 4 times by sigma, right? And what we know is that that is going to be less than or equal to 1 over k squared, right? So that's 1 over 4 squared. 1 over 4 squared gives us 1/16. And so we know that there cannot be more than 1 in 16 students who is scoring outside of this range, right? Either below 100 or above 900. Okay, so 100 corresponds to k equals -4, 900 to k equals +4. And so the probability that you're greater than 4 times sigma is less than or equal to 1 over k squared. K is 4 here, so that's less than or equal to 1 in 16. Okay. Look at another example here. We have workers from a town that have an average daily commute time of 45 minutes. A research report concludes that exactly 84% of commuters have a daily commute time between 30 and 60 minutes. What is the minimum possible standard deviation in this population? So how can we think about this? Well, the first thing to note is what information are we actually given? So we're thinking about this event, the probability that 30 is less than or equal to x, which is less than or equal to 60. And we know that this probability is equal to 0.84 from the report that we have here. Okay, but can we rewrite this probability in terms of distance from the mean, right? If we think about the mean is 45, right? So can we write 30 as equaling 45 plus k times by some standard deviation here, right? And so that's going to be 30. So 45. Oh, yes. No, that's right. So 30 equaling 45 plus k times by sigma. Or we are going to be able to write, say, 60 as 45 plus k times by sigma. Okay. And so what we actually know in both of these cases, right, is that first we are going to want k sigma equaling -15 in this case, right? And if we have over here, k times sigma is going to be equaling +15. Okay. And so if we, because mu, 45 here, is the halfway point between 30 and 60, right? If we just take k to be the same value, except one is minus and one is positive, right? Then we can say we're equally distant, and what we're just trying to solve for is what is this actual sigma value going to be here, okay? And so what we can do is, instead of using sigma and k directly, because we don't know any of these values, right, what we can do is we can turn to the other form of our Chebyshev's inequality. And so we can say that the probability that x minus mu is less than or equal to epsilon has to be greater than or equal to 1 minus sigma squared over k squared, right? And so then ultimately, this is going to allow us to say, or sorry, not sigma squared over k squared, that should be sigma squared over epsilon squared. My apologies. Okay. And so then here, right, we know that epsilon is 15. We're either 15 below or 15 above. And so we know that the probability that x minus mu is less than or equal to 15 has to be greater than or equal to 1 minus sigma squared over 15 squared. Right? But we know this probability, right? This probability is given to us as 0.84. And so then what we can do is, if we take all of this sort of together, we're saying that 0.84 has to be, by Chebyshev's inequality, greater than or equal to 1 minus sigma squared over 15 squared. And now what we can do is we can solve for what sigma squared has to be here, right? And so then if we bring over sigma squared divided by 15 squared, it has to be greater than or equal to 1 minus 0.84. Okay. And then if we rearrange this, right, if we come up here, we can then say that sigma squared has to be greater than or equal to 15 squared times by 1 minus 0.84 is 0.16, which is greater than or equal to 36. Okay, so our variance has to be at least 36, and so that would mean that our standard deviation has to be greater than or equal to 6. Okay, and so to walk through this again, right, because there's a lot sort of going on here, we're given this piece of information right here, right? We're told that this probability is exactly 0.84. And what we can do is we can say, well, this is actually an event of the form x minus mu being less than or equal to epsilon, right? And what is epsilon in this case? Epsilon here has to be 15 because 30 is 15 below our mean, 60 is 15 above our mean. And so we can write that as x minus mu being less than or equal to 15. But by Chebyshev's inequality, we know that has to be at least 1 minus sigma squared over the epsilon, so 15 in this case squared. And so 84% has to be greater than or equal to this threshold. And then at that point, it's using some algebra skills in order to solve for what that means for our standard deviation. Okay? And so working through this calculation or this argument one more time here. Right? So what is the minimum possible standard deviation? Well, by Chebyshev's, we know probability that we're in k standard deviations of the mean has to be greater than or equal to 1 minus 1 over k squared. And so if we want to plug that in terms of epsilons, right, then taking k sigma equals epsilon, that gives us that being less than or equal to epsilon has to be greater than or equal to 1 minus sigma squared over epsilon squared. And so then plug in mu as 45, plug in epsilon as 15. That tells us that 0.84 has to be greater than or equal to 1 minus sigma squared over 15 squared. And then taking epsilon to be 15, that allows us to solve for sigma squared to be 36. And as a result, sigma has to be greater than or equal to 6. Okay? And so this is using it in this different kind of way. But we know that if it's true that the daily commute time is 45 minutes on average, and exactly 84% of people fall between 30 and 60 minutes, then the smallest that the standard deviation can be is 6. Right? It can be larger than that, but the smallest is 6. Look at one example here, another example here. So we have a battery manufacturer that has tested their batteries and finds the average lifespan to be 50 hours. The standard deviation is 5 hours. And they need to report to regulators an interval such that 99% of all of their batteries fall within it. And we want to give them one such interval. And so in other words, right, any interval can be expressed as x minus mu being less than or equal to some particular value, say epsilon. And we want that to have a probability of at least 99%, right? Greater than or equal to 0.99. Okay. But right here, right, this 0.99, we know from Chebyshev's, if we write this as 1 over, say, k squared, and we take epsilon here to be k times by sigma, right, then that's going to be our valid statement here. And so what we can do is we can say, well, let's solve for 1 minus 1 over k squared equaling 0.99, okay? And so then k squared, if we start rearranging this, we get 1 minus 0.99 is equal to 1 over k squared, okay? 1 minus 0.99 is 1%, right? And so then k squared is going to be 1 divided by 0.01, and so then k is going to be equal to the square root of, or 1 divided by the square root of 0.01. Okay, and so then we take k to be this, right? And then what we can say is, well, if you take k times sigma, then that's going to give us our upper and our lower bound here, right? And so then in particular, right, if we take an interval that is going to be the mean minus k, which we had was 1 over the square root of 0.01, times by our standard deviation, which is 5, and then we take the upper bound to be mu plus this same thing, then by Chebyshev's inequality, we know that there has to be at least a 99% chance that this interval will contain the actual truth, right? And so, or that it contains the actual lifespan of the batteries. There's a 99% chance that that happens. So working through this, right, we want probability that x minus mu is less than or equal to epsilon to be greater than or equal to 0.99, right? What this requires is that the probability that it's greater than, if we do the complement, is less than or equal to 0.01. And using Chebyshev's inequality, right, we can write out this alternative complement as probability being greater than or equal to epsilon is less than or equal to sigma squared over epsilon squared, right? And so then just solving this to be 0.1, right, is going to give us epsilon squared. If we multiply through and then divide by that 0.1, we can solve for what epsilon would have to be. Okay, and so epsilon has to be 5 divided by 0.1, which is going to be 15.8. 1. And so then taking the lower bound and the upper bound to be the mean minus that value or the mean plus that value is going to give us at least a 99% chance of falling in this interval. Right, so there was actually a typo in that solution right there, right? Because we wanted it to be less than or equal to 0.01, but we had plugged in 0.1 here. Okay, and so if we solve through this correctly, then we should get epsilon to be 50. And so then we have 50 minus 50 to 50 plus 50, which gives us 0 up to 100. Okay, and so that's going to give us a much cleaner interval here. And this is going to actually be the exact same thing as when we had solved it the other way, right? Because then what we had said was that our interval should be equal to mu minus k, which we had as 1 divided by the square root of 0.01, right, times by sigma as our lower bound. And so that's going to be 50 minus 1 divided by the square root of 0.01 is going to be 10 times by sigma is 5, and so that gives us 0. And then the upper bound is mu plus 1 over the square root, 0.01 times sigma, which is going to be 50 plus 50, or 100. And so what we're saying here is that if you take the interval to be 0 to 100, there is at least a 99% chance that every battery falls within that interval. No matter the distribution of batteries, right, no matter anything else about it, there's always going to be at least a 99% chance. It might be a higher chance than that, right? Perhaps it's going to be the case that all batteries, actually, no battery ever lasts beyond 100 hours, but this is an interval that no matter what, there's a 99% chance based on the standard deviation and the mean. So Chebyshev's inequality provides a distribution-agnostic approach in order for us to bound probabilities that express these symmetric events in terms of deviations from the mean. This is in some sense a weaker empirical rule in the sense that it does not give us approximate probabilities. But on the other hand, it's going to allow us to bound probabilities no matter what distribution we're talking about. As long as you know the mean, and as long as you know the standard deviation, then you're going to be able to apply Chebyshev's inequality to bound these probabilities. And so that's going to be very strong, where in order to use the empirical rule, you do need to know that things are normally distributed. Okay, and so the application of Chebyshev's is going to be wide-reaching, but broadly speaking, it's going to allow us to have these lower bounds or these upper bounds on the probabilities that we're actually looking at.